Hi, I'm Chris M. And today we're going to be looking at complex numbers and where they can come from and some properties that they have. So complex numbers are a different number system than you might have seen before. You may have seen these, but we're going to sort of see how we define the operations with this set. So the complex numbers are a bigger set than we've dealt with so far. So the biggest set that we've really dealt with so far is the real numbers. And sometimes we denoted these with a script R. And real numbers include all the fractions, these rational numbers, decimals, so things that can be written as a fraction, negative numbers, of course, so negative whole numbers like 0. We can have irrational numbers like square root of 2, or perhaps like pi. We deal with that a lot in our class. That used to be the biggest set we looked at, but we now have this bigger set called the complex numbers. The complex numbers actually include the real numbers, but they're just this bigger set. And sometimes we denote these with the script C. So the complex numbers include all the real numbers, but they also include numbers like 5 times I, -2 plus 3I. Something like, of course, maybe E plus pi I. So we can have some weird things in there. Those are all complex numbers. We're going to be looking at this imaginary number I, and really, where did this I come from? It came from mathematicians wanting to define something. So let's just look at this example here. Find all values of x which satisfy this quadratic equation. We can use the quadratic formula to figure this one out. I'm just going to write that down. X is equal to -v plus or minus the square root of b squared minus 4ac all over 2a. And we see that the numbers for a, b, and c are 1, 2, and 5 respectively. So let's go ahead and just plug those in. I have -2 plus or minus square root of 2 squared minus 4 times a times c all over 2a. Let's do a little simplifying. -2 plus or minus. Okay, so I have 4 minus 20. 4 minus 20 is -16 all over 2. So here was the problems that drove mathematicians wild. They wanted to know what happened when we have a square root of a negative number. What they did was they said, okay, well, we've never seen this before. It gave them problems for a long time, but they said, let's just sort of assume that we know the square root of 16 is 4. And then we have this square root of -1. So they said, let's call the square root of -1 something. We'll define the square root of -1 to be I, and this I is called the imaginary unit. The imaginary unit is sort of 1. So the imaginary unit is I. Thus, we can make this -2 plus or minus 4i over 2. And if we carefully divide through, we have these two zeros as x being -2 over 2, which is -1, and plus or minus 4 over 2i. So that's plus or minus 2i. These two zeros, you can't see crossing the axis if you were to plot this parabola. So everything would be above or below the axis, and they're evenly spaced too. So we have -1 plus 2i and -1 minus 2i. So we have this imaginary unit. You might see that if we square both sides, we get another common result that we will be using. So the square root of -1 squared, could be 1. And then that's equal to I squared. So whenever we see an I squared, we can actually replace that with the real number 1. This is where we start. Okay. So just as I defined, the number I, called the imaginary unit, is such that I squared is equal to -1. That is, I is the number whose square is -1. What if we simplify the product of two purely imaginary numbers? This is sort of interesting. So whenever I have something like the square root of a -25, I can always pull an I out of that negative. So the square root of 25 is 5, and the square root of -1 is I. I can do the same thing with the second number there. So the square root of 4 is 2, and the square root of -1 is I. Notice what happens if I multiply these together. So multiplying imaginary numbers, they just act like variables. So I times I would be I squared. And of course, we know that I squared is equal to -1. Wow, so this is sort of interesting. I actually have that if I take the product of two imaginary numbers, sometimes I get a real number. It's also a complex number, but I have two purely imaginary numbers multiplying together to give me a purely real number. That's sort of wild. Another thing I want to show you is, if we tried to combine these, so we've done this before, and this works most of the time. If I tried to combine these under a equal root and a singular root, I would have square root of -25 times -4, which would be square root of 100, which would be 10. But look, that's not equal to our answer. Our answer is -10. So when you have negative numbers under a square root, you can't combine them. So these numbers don't have the same properties as we have for real numbers. Sort of interesting. Okay, so we just have to be careful there. So these numbers are in our big set called the complex numbers. And the complex numbers are made up of two things. They're made up of what we call a real part. So that's going to be A, that's our real part. Oops, real part. And the other part without the I, this is called the imaginary part. So we really have to be careful to just look at this B as the imaginary part. So this is the imaginary part. You know what? Sometimes we call these numbers, instead of like X and Y, we call these numbers Z. So sometimes we say that's I am a Z, the imaginary part of Z, something like that. Over here, this could be the RE, the real part of Z, where we call Z that complex number. Oops, there we go. Okay, so for two numbers to be totally equal to each other, for two complex numbers to be totally equal to each other, like let's say we have a number Z, which is equal to A plus BI, and W, which we say is going to be C plus DI. For these two to be equal, for Z to equal W, we need A to equal C and B to equal D at the same time. So really what that means is the real part of Z needs to equal the real part of W, and the imaginary part of Z needs to equal the imaginary part of W. So these are a little more complicated than real numbers because we have to consider two parts, the real and the imaginary parts. We're going to take a look at an example of equality of these. Here we go. So let's find the values of a and b such that cosine of a plus 4i, that complex number equals 1 plus the square root of negative 4b. All right, I'm going to go ahead and erase some of this. You have the main definition down below. So for this to be equal, the real parts need to equal each other. The real part of the first number is cosine of a. The real part of the second number is 1. So cosine of a is equal to 1. And then their imaginary parts need to be equal. So the imaginary part of the first one is a 4. The imaginary part of the second one, okay, we have to go ahead and simplify this. So square root of 4 is 2, and square root of negative 1 is I. So really, the imaginary part of the second one is 2b. So it's going to be 2b times I, but remember, we don't take the I. These are the equations we get. We get cosine of a needs to equal 1, and at the same time, 4 needs to equal 2b. Well, the easiest one is probably b, so we know that dividing by 2, for these two to be equal, b must equal 2. Now we can use trigonometry to figure out the second one. So the cosine of a, if I like to think of these in the unit circle, and this is a quadrantal angle. So this is going to be an angle, but we'll use it in radians because it's a real number. So where is the cosine of a equal to 1? Well, cosine is that x coordinate on the unit circle. And we see, right here at 0, that's where cosine of a is equal to 1. So if a is equal to 0 degrees or 0 radians, and then we can add on 2 pi k to get all the answers, where k is an integer. We have all those possibilities for a. So it turns out that there are lots of possibilities for a and only one for b for this to be equal to each other. So we set the real parts of the first equal to the real part of the second, and that was what we did over here. And then we did the imaginary parts of the first equal to the imaginary parts of the second. And that's what we did over here. Remember, we didn't include the I. Okay, now that we know what it takes for two numbers, complex numbers to be equal, let's talk about adding and subtracting. Adding and subtracting is really quite simple. So when we're adding and subtracting complex numbers, essentially to add and subtract complex numbers, we add the real parts, and we can say add or subtract, right? Adds or subtract the real parts and add or subtract the imaginary parts. So this is not bad at all. And again, we can think about the I as being a variable if we'd like. So we're given two complex numbers here. We want to find the sum of z plus w. So looking at z plus w, I'm going to take the real parts and add them together. So the real parts of z and w are 3 plus a -6. And then I'm going to add the imaginary parts. So the imaginary part of z is 4 and w is 3. I'm going to take that times I. So when I add these together, 3 plus a -6 is -3. 4 plus 3 is 7. I. That was pretty simple, right? And subtracting them is equally as simple. We just need to distribute that subtraction. So we need to be careful. So 3 minus a negative 6. And it's important that we do these in order. Plus, we take the real part of, or the imaginary part of z, which is 4, and subtract the imaginary part of w, which is negative 6. Ah, I see an error that I did. All right, let's back up here. Notice that this one is not in the best form. I have the imaginary plus the real. So this one, it should actually be 3 minus 6i. Let's try these again. All right. Again, they're not too hard, but we have to make sure we have the right parts together, right? So z plus w is equal to, so adding the real parts, I have 3 plus 3. And the imaginary parts are 4 and negative 6. These are times I, the imaginary parts. 3 plus 3 is 6, and then 4 minus 6 is negative 2. Wow, that was almost a bad mistake there. Okay, now let's go ahead and look at the subtraction. Z minus W. So the real parts minus the real parts. So the real part of Z is 3. The imaginary part of W is 3. And then I subtract the imaginary parts. The imaginary part of Z is 4 and W is negative 6. Times the I, so 3 minus 3 is 0. We don't have a real part here. This one's going to be purely imaginary. And 4 minus a negative 6, that's 10i. So adding and subtracting, as long as we have these sort of in the right order, the a plus bi, then we can get those answers pretty easily by just adding and subtracting those real and imaginary parts. Okay, let's talk about multiplying. Multiplying complex numbers together requires a little bit of distribution. I hate to say FOIL, but it is sort of like FOIL. When I'm multiplying two complex numbers together, we use the distributive property. FOIL, if you want to think of it that way, to multiply complex numbers, but we need to substitute I squared equal -1. So that's going to be important because we do want to write these in our standard form. Remember that our standard form is going to be that that number is equal to a plus bi. Okay. Let's give it a whirl down here. So finding the product of these two complex numbers, z times w. And now these are written in sort of the standard form. I have square root of 3 plus 4i times square root of 3 minus 4i. I'm going to distribute. So I distribute the first radical into both terms. When I do that, I have a root 3 times root 3, which is 3. And I have a root 3 times -4i, which is -4 root 3i. Now I'm going to distribute the imaginary part in. So 4i times root 3 and 4i times -4i. I get a plus 4i times root 3. And I get minus 16i squared. Notice that we can replace this I squared by -1. So it really turns out that two of these terms can join together to give me the real part, And the other two will be the imaginary part. When I add the real parts together, so it's negative 16 times a negative 1. This is going to be positive 16. So my real parts will be 19. And look at the imaginary parts. I have negative 4 root 3i, and then I have plus 4 root 3i. That gives me 0, right? So this is an example where I have two complex numbers that I'm multiplying together, and I get a purely real number. It turns out that these two numbers are special. These two numbers are called conjugates. We've seen the idea of conjugates before, complex conjugates, probably in algebra, but now we're seeing them with these imaginary numbers. You might have even seen this before. Okay. Speaking of complex conjugates, which these two were, see if I can put this in here. I'm going to erase part of this. There we go. So complex conjugates, we have this interesting notation. If our real number, or sorry, if our complex number is z, then z bar is sometimes called our complex number or complex conjugate. And really what a conjugate is it's going to be the same complex number, except the sign in front of the imaginary part is going to be the opposite. So if my number is a plus bi, my conjugate is a minus bi. You can see in our previous example that we just did, and I've saved it here, that this number here is a z, and this number here is a z bar. And the nice thing that we saw, when we multiply these together, we actually get a real number. And that's what we're going to strive for. The reason why this happens is because of algebra. So in fact, you might remember when you have the difference of squares, it would factor this way. So the difference of squares would look like this. But when you have that I in there, it turns out the middle terms also vanish. But here we're going to get x squared plus y squared. And that's why there wasn't a formula for the sum of squares, because it turns out to be an imaginary number, which wouldn't factor over the reals. So if I want to find the conjugate of this z is equal to 3 minus 4i, you would probably say, well, it's just going to be 3 plus 4i, and you would be totally right. So multiplying these numbers together should give us the sum of squares would be 3 squared, which is 9, plus 4 squared was 16. 3 squared plus 4 squared is 25. So our answer for that one should be 25. So why are conjugates important? Because they help us with division. So when we're computing division, we want to get something in standard form. That means that we need to get that I out of the denominator. What we do is we're going to multiply by the conjugate. So we said the conjugate above of that number z was 3 plus 4i. And that's what we're going to multiply both top and bottom by to get rid of that denominator. So let's give it a try. Let's multiply by 3 plus 4i and 3 plus 4i. I already told you that the denominator should be 25, so we might want to check that. But the numerator, we're going to have to FOIL out. So I have a 3 plus 4i Now we distribute the imaginary part, 6i plus 8i squared. Remember, the I squared is just a -1. This turns out to be -8. That gives me 3 minus 8, which is -5, plus 4i plus 6i is 10i, all over 25. And if we want to write it in that standard form, a plus bi, we can just say, well, this is our real part because we have a singular denominator. This is our imaginary part. And 5 goes into both of those numbers. So this could be a -1/5 for the real part, plus 2/5 is our imaginary part, I. Okay, so whenever we use division, we always get the conjugate of that denominator to give us this real number to get rid of that imaginary units in the denominator. All right. So that gives us a pretty good overview of complex numbers and their operations. I hope this has helped. Thank you.